described by a wave equation, which sets out how the disturbance proceeds over time. The mathematical form of this equation depends on the type of wave. Let me break this down for you, the best way that I know how. Hello, I'm Rita, and this is Physics for Show's episode on making waves. A single all-encompassing definition for the term wave is not straightforward. Get it? Let's snap out to my backyard so I can give you another example. There are two main types of waves, mechanical and electromagnetic. Mechanical waves travel through a physical matter. The matter acts as a substance that's being disturbed, much like the water in this pool. The water is translating energy like a medium. What are you supposed to be?
I am a medium. You can call me ether, enlightening ether.
We will be showing you more than you ever wanted to know about waves. We will be making some in our own creative fashion and see what gets created on the scene this time.
Don't mind me. I will just be everywhere, translating energy and such.
Okay, sure, fine.
Sound waves are not easy to see. They propagate via invisible air molecules, colliding with their neighbors. Matter like water makes it easy to see waves as they roll out.
A vibration can be defined as a back and forth motion around a reference value. However, not every vibration is a wave. In an attempt to define the sufficient characteristics that qualify a phenomenon as a wave results in a blurred line. Get it?
I once stayed up all night trying to figure out where the sun went. Then suddenly, it dawned on me.
The difference in origin introduces wave characteristics particular to the properties of the medium involved.
You would like me to get involved? Sure, I would be happy to. First, I would like to predict you need funding. Yes, I am seeing that if these smart YouTube viewers want more videos like this, then you need to find a funding origin. I can see an email address that donors and organizations can contact to discuss episode sponsoring. Can you see it too?
Today, I'll be showing you how to make a wave machine out of Sour Patch Kids. It's going to be very easy and very tasty. First, I need to gather my materials. Duct tape, barbecue sticks, clamps, Sour Patch Kids, and maybe I'll even use a tape measure. this is an example of a standing wave because, as you can see, it goes to a fixed point and then changes direction. Now let's ask Mom if we can eat it. Mom, can we eat it now?
Sure, honey.
Let's eat. Mmm.
Waves normally move in straight lines through a transmission medium.
Waves exhibit other common behaviors like these. I'm going to show you 7 slides regarding these standard situations. Feel free to pause them for more diving ocean deep into the physics of waves.
Those are some strong wave behaviors. That gives me an idea. I will be right back.
Okay, I think it's time to look at some equations. Wavelength can be measured between any 2 corresponding points on a waveform. In the case of a function with a wavelength period, you can solve for that function using this equation here, where lambda is the wavelength, and so a snapshot at any given time, t, we find that the wave is varying periodically in space with a period equal to the wavelength. And to explain the variables, down here we have lambda is the wavelength that's measured in meters. Nu is the wave speed, and this is meters per second. Nu. F, this is the frequency, and it's measured in 1/seconds, so the inverse of seconds is actually hertz. And a capital T here, sometimes it's a lowercase t, is also could be the period in seconds. And now going back up here to the picture, x is the distance along the way for a transverse wave flowing across a distance, and the displacement off of this origin line is that propagation of the wave through space. This photo also has the wavelength showing you from crest to crest, but a wavelength can also go from trough to trough. The bottom of the wave to the next bottom of the wave, those 2 distances would be equal. And then labeled here as y, up the y-axis, is the amplitude. And the amplitude is that distance off of the origin that it keeps alternating between.
Consider a traveling wave on a string. Consider this wave as traveling. Mathematically, the most basic wave is the one-dimensional sine wave, with an amplitude described by the harmonic wave equation. Psi sub k of space and time equals a sub 1 cosine of kx minus omega t, then plus a sub 2 sine of kx minus omega t.
Stop! You're going to put them to sleep! The wave equation also explains a new form of matter, antimatter, previously unsuspected and unobserved, but now experimentally confirmed. Antimatter.
The Schrödinger equation describes the wave-like behavior of particles in quantum mechanics. Solutions of this equation are wave functions which can be used to describe the probability density of a particle. The Dirac equation is a relativistic wave equation detailing three-dimensional electromagnetic wave interactions.
Don't fall asleep. Stay with me. I got this. From quantum mechanics, I need to bring this back to theater. Well, we happen to have our very own acoustical engineer right here on the Physics for Show team. So please meet our musical coordinator and super sound woman, the musical instrument mastermind behind her latest project, debuting in her first solo concert, Miss Allie Amaral.
I really like this tone that I... So what I have here is the bass that I made. I made it with parts from an older bass from before, so it has two pickups here. These are knobs that control the pickups. This is the volume. And so these are pickups that you could normally see in a guitar, so they work through electromagnetism. But then this is a contact mic. So instead of getting picked up through the air, it gets picked up by touch. So when this is on, when I touch it, when I move this, that's how it's going to transfer the sound. This is called an Ebow. So it's going to resonate the strings similarly to a regular bow that you would see on a violin. And it's pretty much a big magnet, which when I hold it above the strings is going to make it vibrate similar. Here is a Midi controller. So I'm going to have this plugged into the computer over here, and it's going to activate a synthesizer that I have on there. So these knobs are going to control the synthesizer. And another thing I have coming from the computer is a looper. So it's going to record the sound that I have coming out of my bass, and it's going to play it again. If I play one note and then I stop it, it's going to play that note over and over. So these 4 buttons will activate the 4 different loopers, and these 4 buttons will stop the loopers. And then over here, I have a guitar pedal. This is a reverb pedal. So it's pretty much going to make everything sound very echoey, just as kind of some ambient sound to give a little bit more depth to the bass. This is the interface, so this is what connects my bass into the computer so I can run it through the program. These are what are changing when I turn these knobs. It changes the harmonics of the note. So like, that's a C being played, and so this is the original C sound. And then these are all like weird harmonic levels, which creates, harmonics are what creates the timbre of instruments.
have time for today. Thanks for tuning in.
Wait, Rita. Whoa, whoa, whoa. How about talking about particle wave duality? Could we do that in the next episode or what? Don't leave me hanging.
Please don't make me do an episode about this. It's really hard to relate it back to theater. Wave, particle. What's in a name? A rose by any other name would smell as sweet.
I have a joke. What did one quantum particle say to the other quantum particle? Nothing. It just waved.